The Rosetta Philae spacecraft that visited 67P Churyumov-Gerasimenko was perhaps ESA's most ambitious mission. NASA isn't the only one that has performed breathtaking missions to other worlds, and personally, the Rosetta mission is ESA's answer that really holds its own against some of the impressive stuff NASA has done. This mission allowed us to see a comet up close for the first time, a visitor that originally came from the Kuiper belt, or the distant belt of comets and asteroids beyond the orbit of Neptune. It was also a groundbreaking mission in that it was able to land a probe on the surface and directly interact with the materials found on the comet. Its discoveries were vast and impressive, and gave us an insight into the far reaches of our solar system, how it formed, and most importantly, did comets once contribute to life on Earth? However, not everything went according to plan with this mission. Philae, the lander part of the mission, was expected to perform scientific experiments on the surface of the comet for 5 months, but it didn't manage anywhere near that. So what went wrong? I'm Alex McColgan and you're watching Astrum, and together we'll find out everything that the Rosetta Philae mission did and discovered around 67P Churyumov-Gerasimenko. (67P) is currently a Jupiter family comet, meaning its orbit doesn't take it much further out than Jupiter anymore, although it was once a Kuiper belt object, which means it originated beyond the orbit of Neptune. The Rosetta Philae mission launched on the 2nd of March 2004 on board ESA's own Ariane 5 rocket. It was initially set to be launched on the 12th of January 2003 and had a totally different target. But the Ariane 5 rocket program had a major failure a few months previously with another mission, meaning all launches were grounded until they could determine and fix the problem. With the launch window for that comet missed, a new target had to be chosen, and ESA settled on 67P due to the ideal position in its orbit. Once in space, the Rosetta spacecraft had an eventful 7-year journey on its way to the comet. As is often the case with missions to the outer solar system, it needed some gravity assist to get that far out. It had a flyby of Earth in 2005, and then a flyby of Mars in 2007. This Mars flyby was pretty risky. It would skim the planet just 250 kilometers above Mars's surface. Also, during this flyby, which lasted 15 minutes, it would be completely in Mars's shadow, and because the craft is solar powered, the craft had to go into standby mode. Rosetta's components had to be kept warm by onboard electric heaters to avoid damage from the harsh environment of space. However, its batteries were never designed to run by themselves for long. Its power levels got dangerously low, and had they completely drained, then it would never have been able to switch itself back on after the flyby. Nothing could be transmitted back to Earth as this was happening, so mission controllers simply had to wait and hope the spacecraft would turn itself back on. They called this the €1 billion gamble. But the flyby was a success, and the mission continued on, even managing to capture some photos of Mars in the process. The spacecraft flew by Earth a second time in 2007 at a distance of 5,700 kilometers. Interestingly, during this flyby, it was spotted by ground-based telescopes and was presumed to be a near-Earth asteroid, and so was added to the Catalina Sky Survey as a 20-meter potential Earth-impacted asteroid. It wasn't until a few days later that the mistake was found. Heading back into the solar system with increased speed from the flyby, its trajectory took it past 2867 Steins, a small 5-kilometer asteroid in the asteroid belt beyond the orbit of Mars, and these are some of the pictures it took. Rosetta did one final flyby of Earth in 2009, which finally gave it the boost it needed to reach the comet. During this last leg of the journey in 2010, it flew by another asteroid called 21 Lutetia, which is 100 kilometers in diameter. I think seeing both of these asteroids gives an interesting comparison between asteroids and comets, because as you are about to see, they look remarkably different. After visiting Lutetia, the spacecraft went into hibernation mode until 2014, when it started to approach the 4.5 kilometer wide comet Churyumov-gerasimenko for the first time. After a number of burns with onboard thrusters, they aligned the trajectory of Rosetta with the trajectory of the comet. As Rosetta approached, these fantastic images started to come in, and they surprised everyone. The comet seemed to actually be a contact binary, full of jagged edges and sharp sides, cliffs, valleys, and crevices. It's a breathtaking sight to behold, and is really a lot more interesting looking than anyone had previously thought. But upon seeing these images, mission planners collectively thought, how are we going to land on this? You see, the Rosetta Philae mission has two parts: the orbiter, Rosetta, or the mothership of this mission, and a much smaller lander probe, Philae. Mission planners wanted Philae to land on the surface in order to closely examine materials making up the comet with a variety of different scientific instruments. They couldn't afford to have it fall over on its back upon landing, thus not providing any scientific data about this special object. So the first thing Rosetta did upon entering orbit was to map the unusual surface of the comet to find the ideal landing site. Apart from the non-spherical nature of the comet, another thing to consider was the amount of outgassing at any particular site. You see, some parts of comets are very active, with lots of water being ejected into space, especially as the comet approaches the Sun. This water outgassing into space is what forms the defining characteristics of a comet, its unique halo and tail. Landing on an outgassing site was seen as too dangerous for the health of the Philae lander, so a less active site was chosen. So, on the 12th of November 2014, Philae was ejected from the Rosetta mothership and started its extremely slow descent towards this section of the comet. Philae was equipped with 2 harpoons, which were due to shoot into the surface to stop the probe from bouncing on impact, as the escape velocity of the comet is only 1 meter per second. To give you some perspective, if you were standing on its surface, you could probably jump off it altogether. Its gravity would be too weak to pull you back. There was eager anticipation and nervousness at mission control as Philae descended, as due to all the many different factors, like the shape of the object, the outgassing, and the stray bits of comet debris in orbit around the comet, there was a lot that could go wrong. Philae eventually touched down on the surface, and as the spacecraft landed, it sent back a landing signal to mission control to say, "Job well done." What mission control didn't realize at that moment though, was that their worst case scenario had just happened. The onboard harpoons hadn't fired, and although the probe had landed, it immediately bounced off the comet's surface. Commands were sent to it to start performing scientific experiments, but Philae was actually floating in space at that moment. There was a serious amount of confusion for a while, until they realized it hadn't properly come to a rest, and was still in the process of bouncing. Luckily, the bounce's velocity was only 38 centimeters per second, meaning that it only rose 1 kilometer from the surface before eventually coming back down again. Over the course of 2 hours, it bounced 3 times before eventually coming to a rest. Sadly though, it was well away from its initial landing site, and came to rest here in a region that was often obscured from the sun, meaning it would quickly run out of power due to its solar panels not getting much light. On the other hand, mission controllers felt extremely fortunate that it had appeared to land the right way up, so that it could still collect at least some valuable scientific data. Mission controllers suddenly had a rush on their hands to collect as much scientific data as possible before the batteries ran out. Their estimated 5-month mission was suddenly cut down to less than 60 hours. By the 14th of November, battery power had run out and communication was lost. Amazingly, in June 2015, with increased exposure to the sun due to the comet's closer approach during its orbit, the little Philae lander was able to turn on again and sent a signal back to Rosetta. Although the signal was intermittent, the lander was able to perform one last science experiment, which was the CONSERT radar experiment, and it sent back its results. As time went on though, the comet became more active as it got closer to the Sun. It originally only outgassed 500 grams of water and dust per second, but at this point it was outgassing 300 kilograms per second, which meant that in order to keep Rosetta safe, it had to orbit further and further out. By the 9th of July, Philae transmitted its last signal, and then went quiet forever. It wasn't until September that mission controllers eventually found the final resting place for Philae. You can see its legs sticking out just by here. Knowing where Philae landed was important, as it would put the scientific data it collected into perspective. So, what did Philae discover while on the surface? Did it put those 60 hours to good use? And what about Rosetta from orbit? Was it able to make some groundbreaking discoveries? Arriving at this comet was a revelation to mission planners by itself. So far, nothing in the solar system that had been examined closely looks anything like 67P. It's about 5 kilometers across at its longest point, and has 2 lobes which are joined by a narrow stretch of material in the middle. This by itself was somewhat unusual, but it is also very jagged, unlike a lot of asteroids that we visited. During the course of the mission, it was discovered that the surface of this comet is quite changeable. If we look closely at the neck connecting the 2 lobes, it becomes apparent that this section is under mechanical stress. If we look at these rocks, we can see that there are fracture lines running through them. Fracture lines are also apparent from a different angle. Scientists have used models based on fracture lines found all around the neck region to determine that these fractures permeate deeply inside the comet, up to 500 meters below the surface. It seems that as the comet rotates about its axis, the 2 lobes are pulling away from each other, thinning the neck region gradually over time. Huge 10-meter boulders were observed being displaced by this mechanical stress, as well as from the volatility on the surface, sometimes by up to 100 meters due to the comet's weak gravity. This also implies that the comet is really quite brittle and porous, which is something that wasn't known about comets before this mission. As well as fracture lines, layers can also be seen, implying that during its formation, this comet was built up gradually over time. However, even though it is brittle, the surface of the comet is a lot harder than expected. Scientists thought the initial landing site for Philae would almost be soft and fluffy, kind of like a dirty snow, but this was not the case. As Philae came to land on 67P to directly interact with the comet, it found that its final resting location was solid, thought to be water ice, with a thin layer of dust. Mission controllers for Philae tried to get a sample of the soil, but as you can see, it was eventually found out that Philae ended up at an awkward angle, and so wasn't able to get its drill into the surface. However, readings were still able to be obtained by examining the material on the craft itself, which had ended up on Philae after the bounces. Of the surface material examined, it was determined that there were 16 different organic compounds, 4 of which had never been detected on a comet before. While organic compounds do not mean life, life is based on organic compounds. While Philae wasn't able to get too many readings of the surface, Rosetta was also able to get some samples of the comet by collecting some of the dust snow that was ejected away from the comet itself into space. One of the most impressive shots Rosetta was able to take is this video of dust particles and cosmic rays shooting off in all directions, with the stars moving in the background. All the particles are visible because Rosetta is looking at the night side of the comet, meaning increased exposure of the camera can pick up these interesting visual elements. Throughout the mission, Rosetta collected roughly 31,000 dust particles, and interestingly, their composition didn't change throughout the course of the mission, even as the comet became more active, meaning that the whole nucleus of the comet is likely to be consistent throughout. The dust particles consisted of complex, organic, carbonaceous material mixed in with sodium, magnesium, aluminium, silicon, calcium, and iron. What separates this material from an asteroid's, however, is the presence of an abundance of hydrogen and oxygen. It is theorized that asteroids have been heated a lot longer than comets due to their closer proximity to the Sun, which has stripped the hydrogen from their compositions. Comets, however, have been kept away from the inner solar system for much of their lives, meaning these dust samples are pristine relics from the formation of the solar system, and potentially even the molecular cloud the Sun would have originated from. Oxygen was an unexpected find, as it's highly reactive, and if there is hydrogen around, it will usually bind together to form H2O. Carbon and hydrogen were also detected in the comet's tenuous atmosphere by Philae. The dust particles you see here are tiny. The biggest that was collected was only 2 millimeters across. But interestingly, it is particles just like these ones that light up the sky during a meteor shower here on Earth. What these views do give us, though, is an insight into the material that formed the solar system, so we can see where our solar system evolved from. Comets tend to be very dark, only reflecting 3 to 4% of the sunlight that falls on them, which you maybe wouldn't expect from something that is considered to be icy. But actually, not a lot of the ice in a comet is exposed to the surface directly. Most of the comet is coated in this layer of complex carbonaceous dust, which is darker than asphalt. These colored sections in this time-lapse show the exposed water ice. As you can see, it's not a very big percentage of the comet itself. Light that isn't reflected is instead absorbed, heating the volatile material beneath the dust layer, causing outgassing of water and carbon dioxide, which also blasts the tiny dust particles Rosetta picked up into space. As these are ejected at escape velocity, they fall behind the comet and form its tail. Zooming out a little bit and looking at comets generally, let's talk about why comets have two tails. One tail follows the orbit of the comet. This tail is the dust tail. The dust tail is illuminated as sunlight reflects off it. The other tail consists of the volatile material, the water and carbon dioxide that outgassed from the comet. This tail follows the direction of the solar wind, and these particles are illuminated through ionization and interactions with the charged particles from the Sun. It is often hard to see comets with your naked eye on Earth, but every so often a comet will outgas enough material that it is visible. In the northern hemisphere, the last bright one I saw was Hale-Bopp in 1997 when I was just a kid. But I did also recently see Comet Neowise in 2020. What an amazing sight it was. You guys in the southern hemisphere have been a bit luckier with comets. You've had Comet McNaught in 2007 and Comet Lovejoy in 2011. Going back to 67P, there was one other very big reason why the Rosetta Philae mission happened in the first place, and that was to see if water on comets is the source of water on Earth. Before this mission, the theory was that Earth was bombarded by comets early in its development, back when the solar system was a lot more chaotic. Considering a large portion of comets are water ice, these could have given the surface of Earth the water we enjoy today. But as it turns out from Philae's findings, this was not the case. Scientists were able to determine this from the water vapor's deuterium ratio to hydrogen, which is significantly different from Earth's. Deuterium is an isotope of hydrogen with an added neutron. The ratio of deuterium to hydrogen in water is a key to determining where in the solar system an object originated. Here's Earth's ratio, and here's 67P's. As you can see, they are very different. Only 2 comets have had their water vapor measured for deuterium directly, 67P and Halley's comet, and neither suggest that comets were the source of water on Earth. Instead, this data gives more weight to models that suggest asteroids are the source of water on Earth, even though their water content is generally very low. But perhaps there was more water on them billions of years ago. Maybe we simply don't see that much water now because all the volatile substances on asteroids have already burned off. In any case, it seems that Earth would have had a rough time during its formation. Rosetta and Philae were also equipped to detect if the comet had a magnetic field. Initially, scientists thought they discovered the presence of a magnetic field on the comet, the hum of which they converted to audio sound. This is what it sounds like. However, it turns out that this was not the result of a magnetic field, as Philae could not detect the presence of a magnetic field on the surface, but rather this sound is the solar wind's interaction with the comet's atmosphere. In fact, because of this interaction, the atmosphere and comet nucleus are completely devoid of any magnetic field, which is called a diamagnetic cavity. Rosetta finished its mission by crashing into the surface of the comet. As the comet was going further away from the Sun, there was no guarantee it would have enough power for its heaters. So in order to maximize the science gained, mission controllers commanded it to perform a controlled descent into the comet. During this descent, it took multiple images, which you can see in this time-lapse, providing better resolutions of the comet than ever before. Until it finally hit the surface and all communication was lost. Between Rosetta and Philae, they have opened our eyes to what the solar system was like during its formation, and have provided data that has and will yet lead to many discoveries. Here's hoping for many more missions like this one in the future. Space exploration is getting exciting. Thanks for watching. A big thank you as always to those of you that support the channel through Patreon and those that like and share the videos. I really enjoy making them, and your support means I can continue to make more in the future. If you like this video, you'll probably like my other spacecraft videos, so check them out. All the best, and see you next time.